No sound.
It works.
Oh,
Maybe
oh.
you just arrange it.
Boh, vabbè, now it's okay, right? Okay. Okay, so first of all, I want to thank the organizer, Vladimir, Andreas, and Giuliano for the invitation. The title is this one, so I will discuss some geometrical observable in statistical mechanics, so in particular percolation, and then I'll see also the Ising model, but the Ising model will be more like a byproduct of what I'm doing. So we already heard the talk about percolation by Paul today. So this is based on two works. One is of last year, and the other one appeared recently on the archive. And they are both in collaboration with Giacomo Gurarie, who is a postdoc in Italy, in Padova. Before was in Sissa, Trieste. Okay, right. So let me start. So we'll introduce this paradigmatic model of statistical mechanics, which is percolation. So percolation is an interesting, at the same time, dull problem in a way. So you can basically construct a matrix. This matrix is L times L. The matrix can be rectangular, can be square matrix, whatever. And then you color the elements of the matrix with a certain probability P. So for instance, in red with probability P, and in blue with probability 1 minus P, and it's very easy. It was a few, I don't know, milliseconds for a computer to produce this picture. So it's a very simple problem to generate on a computer. So it seems quite dull, I would say. But the fact is that it's interesting because it's an example of a geometric phase transition. So basically, if you increase this probability P, at a certain point, all the elements of the matrix will be red. And of course, there will be a special value, P equal PC, after which basically you generate a giant component of connected cluster or connected lattice sites in the matrix, which I color in green here. So for critical values of this probability, there is a P equal PC. There is a finite probability for any bulk point to be connected to the boundary of the matrix in the thermodynamic limit. So there is a path of lattice sites. So the interesting fact is that there is you can define critical exponent. Critical exponent means that the phase transition is second order, and it was also pointed out some times ago actually that the cluster has to be scale invariant and actually conformal invariant. So there is an example of conformal invariance into this mech that you can generate on a computer very easily. So that's why it's nice. So the critical exponent of 2D percolation, they were studied again long ago by combining some heuristic techniques. Basically, it was called Coulomb gas, date back to the 80s essentially, and let's say the pioneering seminal work on conformal field theory by Belavin, Polyakov, and Zamolodov. So combining some heuristic argument and the ideas which were contained in this essentially revolutionary paper, people, they argued the values of the critical exponent for 2D percolation. And in particular, as an example, a sort of textbook example, as I said, the probability to be connected to the boundary vanishes for values of small p, which is let's say the probability of coloring the sites in a certain way, vanishing at p equal pc as this exponent, 5 over 36. So yeah, right. Essentially, p goes to pc from plus, otherwise it doesn't make sense. Oh, okay, but here I forgot to write p goes to pc from plus. Yeah, but I think better to put. Otherwise, it doesn't make sense. Actually, it is strictly speaking, zero. It's not even a number. Okay, I mean zero. All right. So then, however, somehow the fact which is not probably completely well emphasized is that the partition function of percolation, if you take this L times L matrix and you have free boundary condition, I mean, it's a matrix with free boundary condition, it's 1. I mean, it doesn't depend on anything in particular because it's a normalization of probability. So essentially, it doesn't depend in particular on the dimension of the matrix, which means that if you know, right, the connection between finite size scaling of the free energy and the central charge in conformal field theory, the central charge has to be 0 because it doesn't depend on finite size effect, essentially. All right, this has very, so this is the crucial point, essentially, of the model, the complicancy that you have. So this innocent model is actually very complicated because of this. And okay, as I said, there were many influential works on the connection between quantum field theory and percolation, Coulomb gas, and of course this very important work by Dutsenko and Fatih also. All right, so I think at least to my taste, I would say the one of the nicest results in percolation is this famous Cardy formula, because which was an important contribution by John Cardy back in the 90s. So because basically before Cardy formula, all the observable that they were known for percolation, they were critical exponent. So John Cardy was, I think, the first one actually to basically use conformal field theory, and in particular boundary conformal field theory, which he developed, to calculate a correlation function at c equals 0, which had a physical meaning. So it was not just critical exponent, but was really a correlation function. So something that it's a structure of this, the whole spectrum of the theory, essentially. And Cardy formula is a formula for the probability of having a vertical cluster, for instance, which spans the horizontal sides of the matrix. So, you know, you have some pi v is the probability of having such configuration. Sorry, it's a function. So eta, yeah, is an elliptic function. So eta here is the cross ratio, and is a function, quite complicated function. I mean, I didn't write it here. It's non-function of the aspect ratio. So if you know the aspect ratio, you is an elliptic integral, basically. Okay, so eta is something that you know. If you know the aspect ratio, you plug into this formula, you know what is the probability of having such configuration in percolation that you can measure. Yeah, of course, this is from 0 to 1. Yeah, he knows, I mean, he wrote the right formula. Yeah. Sorry, it's always at p equal pc. Nobody generalized this. Well, actually, with Aldo, we did it. Sorry, we did some, yeah. But it's complicated for p larger than pc. Well, for p larger than pc, this is essentially 1 plus exponential correction, and because its probability is basically 1 if p is larger than pc, of crossing, having a huge cluster which touch the two horizontal, of course also vertical. It was generalized in many ways actually, but that's the first result, and was proven mathematically, so in a rigorous way, with a beautiful formula. It was proven mathematically rigorously by Smirnov, who won the Fields Medal, basically for his works about. Wrong year. Maybe it's so maybe it was 2010. I don't know. The paper is of 2009. Okay, so I didn't say one in 2009. Okay, so right. So basically, that's an interesting result, and it was generalized in many ways later. People, Gerald Watts computed the probability of having vertical and horizontal crossing, etc. Was all of this family of functions, they are called crossing probabilities, essentially. So another important, I think, observation about the quantum field theory, which describes putative quantum field theory, which describes percolation and in particular C equals 0, C is a central charge, was done by Gurarie and Ludwig, based on some observation by Gurarie before, actually. So the idea is the following. So suppose that I have a disk or whatever domain. Sorry? I will tell you. Okay, so there is a finite domain here, and this is a finite domain in two-dimensional planar finite domain, and we have a C equals 0 CFT here. So it can be percolation, for instance, okay? And we insert two operators at the boundary. So these are operators in the field theory. We insert it at the boundary. So of course, I mean, when you have two operators at the boundary, H is a scaling dimension, is chiral scaling dimension of phi. So when you have two operators at the boundary, you can map them to the upper half plane because its theory is conformal invariant. And you can ask what is the operator product expansion of these two fields. So x2, I call it z in the upper half plane, so it's real actually. I mean, you map the boundary to the real axis. And x1, it will be mapped in 0. Okay, so when we do the operator product expansion of these two fields, they have the same scaling dimension, they are chiral, they are inserted at the boundary. There is an obvious problem when C is 0, because the operator product expansion is not well defined. Because if H is different from 0, the field has some non-vanishing scaling dimension, this term is divergent, and is the term which is coupled to the stress energy tensor. So I mean, it's a serious problem with the quantum field theory, because the field, the identity family is strictly speaking not well defined at C equals 0. So that was the observation. Well, actually, this observation has probably was not due to them, but what they proposed was actually that studying, for instance, some differential equation at C equals 0, that you have to regularize the operator product expansion. And a way to do this is to assume that there should be another field, that you forgot it, that has the same dimension as the stress energy tensor, so it has dimension 2, and it enters here in this ellipsis essentially, and cancel, subtract the divergence. But when this happens, automatically you can show that the OP has a logarithmic singularity. So the logarithmic singularity is allowed by conformal invariance, but it's rather specific. You don't encounter all the time, essentially never in minimal models or in unitary theory. So there is this log. This log is needed to regularize the OP at C equals 0 in the identity channel, and it comes with a coefficient that was historically yeah, sorry, I'll come to that. So the small t is the field that has to enter in this OP to regularize it has dimension 2, the same as the stress energy tensor, and subtract this divergence, and essentially the prefactor here gets sort of renormalized, if you want, and historically they call it H over B. So in constant with C, now C equals 0, you have a new number B which parameterize this operator product expansion. But this B was not really fixed by the theory. I mean, C equals 0, you can have many B. So it's not that. So this was conjectured, actually. And I think it's fair to say that there was no any correlation function at C equals 0 where you could see explicitly, well, physical correlation function. Of course, if you look formally, you find many of them, but physically, no fully explicit correlation function has been calculated where you see this B. Okay, that's true. I mean, I think it's fair to say. Okay, so I will show an example where we can actually have access to some physical correlation function where you see this logarithmic behavior at C equals 0. So that's the purpose of this talk, essentially. I forget some. Okay, so now, yeah, an important thing is that notice is that if H is 0, there is no logarithmic singularity. So if H is 0, it's not needed to have a logarithmic singularity. And Cardy formula, there is no log because H is precisely 0. So it's a probability, so it's a pure number, and that means that essentially the conformal dimension of the operator that have to enter there is 0. So that's why in Cardy formula you don't see this log. And basically in all the crossing probability you don't see this log because they are all constructed with operator with 0 dimension. Okay? All right, so now let me introduce a useful tool to construct such geometrical objects which have logarithmic singularities at the critical point. So the useful device is Q-state Potts model. So it was also discussed today, but briefly I recall you. This is a generalization of the Ising model in which you have lattice sites that can take Q value, so from 1 to Q. Q is an integer. And the interaction is colorless. So it means that it's a delta, Kronecker delta over the lattice variable. So it doesn't matter if the variable have a certain color, it only matters if they have equal or different colors. Okay, so that's the Hamiltonian. And it's ferromagnetic, so J is positive. So basically, okay, that's a very famous, there is a very famous rewriting of the partition function in terms of graphs. So you have, so you can expand the partition function in graphs that are basically the percolation graphs. It's like really an expansion into percolation clusters with the measure which is p to the number of bonds. Bonds means the edge which is occupied. P is related to J by this formula. And 1 minus P to the number of empty bonds. So this sums to 1, okay, is the percolation partition function. But the difference if you expand the Q-color Potts model in graphs, the partition function also the configuration, they also come with a weight which is Q to the number of clusters. So this Q is this number. Right, exactly. The connected components that you have. So if Q is 1, that's true, is really percolation. If Q is 2, is the Ising model. But in general, you can construct such random process where the graphs, they are weighted by this measure. Okay?
Strictly speaking, you mean Q approaches 1 as a limit.
Yeah.
Because 1 is trivial. So
Q equal 1, this partition function is truly 1.
yeah, but to have a
Well, it depends what you calculate. But in general, it's true that you have to calculate the limit Q. There are observable, there are, yeah, there,
After some analytic continuation.
yeah, but there are observables, they are also well defined at Q equal 1. I mean, in Cardy probability is some function that you really write.
The Potts model is not defined with Q.
Q equal 1, yeah, the Potts model is strictly speaking is trivial for Q equal 1. So in the sense of the Potts model, you have to take the limit Q goes to 1. All right, but okay, for the CFT, that sometimes is useful, some other, in some other cases they are observable, they are well defined already at Q equal 1. Okay, so for instance, this Cardy formula is one example. All right, so yeah, that's the Potts model, and having this in mind, that's the observable that we are going to consider. So we mark a certain number of points at the boundary of this finite domain. They can be n, for instance. And then we ask the question how they are partitioned into clusters. So you have the total number of partition of n points basically gives you an upper bound on the total number of non-trivial functions that you have to calculate. So I can have a probability that, for instance, 2 are connected with together and 1 with 4. So here they are all connected together. So that's the observable. So we are asking in how many ways they are partitioned and what is the probability that this happen with the measure which I wrote before. So basically, you have many, I mean, the total number of functions that you have to compute is the number of partitions, but they are not linearly independent because of some rules of probabilities. So the number of linearly independent functions that you have to calculate is the number of non-singleton, non-crossing partition, which means that the partition that you have to choose for the points, they have not to contain isolated points. So 4, for instance, cannot be alone. Otherwise, I can reduce this function to another function in which they are all together. So that's basically the dimension of the space of function that you have to calculate. So for instance, the simplest example, n equal 4. So n equal 3, you have only one function, is a constant. It was calculated by Kleban, actually, and Simmons. So the first sort of, let's say, interesting example is perhaps n equal 4. So you have 4 points at the boundary and 3 linearly independent functions. That they are the probability that one is connected with 2, 4 with 3, 1 with 4, 2 with 3, and all together. Okay, so that's are the 3 functions, the 3 linearly independent connectivities that geometrically are associated to probabilities of partitioning points at the boundary in the Q-state Potts model, in percolation, in the Ising model. So I will calculate these 3 functions essentially, or actually something else. So what I will calculate, and that's the result, so I will state the result before entering into the technical details. There will be not much technical details, but some part on conformal field theory. So that's the result. Essentially, from these 3 functions here, which are the 3 linearly independent connectivities, I can calculate a ratio, which is, again, this is a number because it's a ratio of probabilities. It's a pure number between 0 and 1. You see the denominator is less than the numerator, okay? So it's a number from 0 and 1. And I can calculate exactly such number at the critical point is the ratio between this particular combination. This is a normalization. And the nice fact is that, so this quantity has, let's say, has, I would say, 2 nice features. The first one is that you can calculate it exactly. So here are the plots. It's a summary essentially. So that's for percolation, Ising, Q equal 3 pots model, Q equal 4 pots model. So you see that it depends only on one variable, eta. So in principle, it could depend on 4 because you have 4 points. But by conformal invariance, it only depends on the cross ratio, right? So that's, you have only one variable. And from 0 and 1, because the points, they are ordered at the boundary. So when you specify that, for instance, x2 runs from x1 and x3, eta goes from 0 to 1. So that's the thing. So that depends only on the cross ratio. Here, the points can be mapped to the upper half plane, and from the upper half plane, they can be mapped back in any geometry by means of conformal invariance, which means that it's also nice because if you want to check the prediction of conformal symmetry, you can do Monte Carlo simulation, for instance, on a triangular lattice. It's the cross ratio. That's the cross ratio. Cross ratio. It was still a cross ratio, but not exactly the same. The expression in terms of the geometry is slightly different. Okay? But it's conventional to call the cross ratio eta, or x probably. So anyway, so the nice fact is that you can map this in any geometry, and in particular, you can run simulation on triangular lattice by Schwarz-Christoffel transformation. Then you can check the formulas on a triangular lattice. And I will show you the agreement. Third point, before going into the details, this function has a logarithmic singularity at q equal 1 here. So here there is a logarithmic singularity for eta goes to 0 for this function. This logarithmic singularity is fully explicit. And that q equal 2 is also logarithmic, and the logarithmic singularity is here for eta approaching 1. Yeah. That's the analytical. I will show you the numerical later. Okay. It will come. But it's in the paper. Yes. The second one. Okay, so let's go to the details, but I will give you this analytical form. They are quite complicated. I mean, it's not totally. Okay, so let me give some details of the derivation. CFT is a conformal field theory, right? So let me start by recalling the quantum field theory which describe the Q-color Potts model. So that's was essentially analyzed by Tsenko and Fatiev, I think, in the early days of conformal field theory. So the central charge is given by this formula, 1 minus 6 p plus 1, and Q is related to p by this formula here. So Q for me will be always integer. So in particular, I will always only consider the case p equal 2, which correspond to q equal 1, p equal 3, which correspond to q equal 2, p equal 5, which correspond to q equal 3, and p equal infinity, the limit, which correspond to q equal 1, q equal 4, and c equal 1. But in principle, you could consider also non-integer values of q, but I think it's not, for that case, I don't have a nice analytical expression. But in principle, this can be done. For q larger than 4, is no more critical. The model has a first order phase transition. So, all right, so that's the spectrum. You can read the operator content from the Katz table. And in particular, the scaling dimension of the operators that you inserted the boundary. Remember that my operators, they are always inserted at the boundary, never in the back, because this is easier. They have to fit this formula, which is called Katz formula. And in particular, they are chiral. I mean, there is no H bar. They have only, because they are operator at the boundary. So for instance, this is a matrix which contains this integer H, this rational HRS. R and S, they are positive. No, they are non-negative. No, they are positive, and they are positive integer. I will not consider other cases. That's enough for my purposes. So this is the table that you have at q equal 2, so c equal 1/2. And the minimal Ising, what typically is considered in application of Z2 invariant theory is this, well, contains the identity or field with dimension 1/2, other field with dimension 1/16. Sorry.
Again, this theory is not unitary, it's not rational, this is not the usual Ising model. You mean Q goes
Yeah.
to 2 in the
Yeah. So yeah, I will say this now. So here it's the minimal theory, but actually what we will be interested in is an extension of this Katz table, as Paul was saying also today. And in particular, I'm going to consider operators which are on the first column here. So it's an extension, all right? And it's not the minimalism. So to describe geometrical objects, you have to extend the Katz table. This was understood also by Paul, Zuber, and Rasmussen, right? Okay, so anyway, in particular, I'm interested in these operators which are on the first column, and I will focus on the operator which have this label, phi 1 2s plus 1, so the identity, phi 1 3 is the field which dimension 1/2 at q equal 2, 1/3 at q equal 1, and phi 1 5, etc. Because they have a nice interpretation in terms of cluster. So the field phi 1 2s plus 1, when inserted at the boundary, anchors essentially S cluster at the point x. So you have S cluster meeting at x, the boundary point, if there you insert the field phi 1 2s plus 1. Okay, so that's why if I want to calculate connectivities, I have to look at 4-point function of phi 1 3, because I want one cluster which enters at the point x. So that's the field phi 1 3 that has to be inserted according to this interpretation, which again dates back to watermelon exponent by Salaire and Duplantier, essentially. But it has many verifications. So here you insert, you want to calculate the 4-point function of phi 1 3, inserted at the boundary of this domain, in which here you have a random process, percolation, extended Ising model, etc. And you see, if you want to connect this cluster together, you have only 3 possibilities, which agree with the geometrical interpretation that you have 3 linearly independent functions that comes from the correlation function of phi 1 3, or 4 field phi 1 3 inserted at the boundary. So as a matter of fact, again, using conformal invariance, this I can map to the upper half plane. And the correlation function of phi 1 3 on the upper half plane, I can write it like this. So there is a dimension full prefactor. Z is a point on the real axis, which is the mapping of the point at the boundary. So x1 is mapped to z1, x2 to z2, etc. And the 4-point function of phi 1 3 is related to this. Basically, it has to expand over these 3 functions here, this 3 connectivity here. H is h13, is the conformal dimension of this field. And okay, the 4-point function has a standard form. It is a dimension full prefactor and some adimensional function which depends on the cross ratio. This is upper half plane. So this is computed in the upper half plane. So I map this geometry into the upper half plane, and I calculate here the correlation function. And this is called conformal block. So this function here is called also conformal block. It has meaning, algebraic meaning, because you can calculate expanding over all the descendants of the Virasoro algebra. So that's also, all right. So the point which is important here is that this function g solves a third order differential equation. That comes again from this fundamental work of Belavin, Polyakov, and Zamolodchikov, because the field is degenerate at level 3, so there is a null vector, and you can write differential equation for phi 1, 3. And the differential equation has degree 3. It means that it has 3 linearly independent solutions, and you have to understand basically how relate the 3 linearly independent solutions to these three functions. So that's the task. You have to do this. Okay, so that's the differential equation. I write it here. And it's quite complicated, you see. It's not easy differential equation. And I want to relate basically the geometrical objects, which are these connectivities, which I know they are linearly independent, and then I also know they are solution of this differential equation. G parameterize this differential. I mean, the p's, they are related to G by the formula that I wrote before. Yeah. I will fix this by looking at the singularities of and I will fix essentially the coefficient in the, I will fix the coefficient in the linear combination by looking at this. So the basis, it's a differential equation, so there is a degree 3, there is a three-dimensional space spanned by the solution, and you have 3 bases. So the first basis, which is the basis which is easy to work with, is the Frobenius series. Because, you have a differential equation, there are singular points, regular singularities, and then you can write the Frobenius series. And the Frobenius series, you can implement it easily in Mathematica. You can go up to 10 to the 5 coefficient, 1 million coefficient. It's easy to implement Frobenius series, Sorry? Well, it's this series. Well, you have a regular singularities at 0, 1, at infinity. Yeah, well, it's called Frobenius series because this exponent can be not necessarily integer, I mean, of course, traditionally in books of ordinary differential equation, they call Frobenius method. So maybe I should call it Frobenius method, but it's just a power series solution of this differential equation. I mean, it's something, of course, not complicated. But generally rho can be non-integer, so okay, you call it Frobenius series. that's rho is the exponent which comes from the initial equation of the differential equation. So for any rho solves a cubic equation because it's a third order differential equation. So rho parameterizes a particular solution of the differential. I mean, this is quite standard. Okay, then you have other basis which is given by the conformal blocks. There is a formula, remarkable formula, which was discovered by Alexei Zamolodchikov to calculate recursively the conformal blocks. So you have also another possible basis for the solution of the differential equation. And then, of course, there is this geometrical basis which we have to identify. So typically, these two are equal if you don't have roots of the initial equation which are separated by integers. If the roots, they are not separated by integer, the basis, the Frobenius series, the power series expansion coincide with the conformal block. But otherwise, is not always true, and that's the case here. So you have to be a little bit careful in identifying the power series solution with the conformal block if this number rho is an integer. Well, if you have roots which are separated by integers. Okay, sorry, I will go fast now. So here so that's the cubic equation for rho. So you have three solutions which correspond to the operator product expansion of the field phi 1 3 at the boundary. So rho can be 0, which means that you have no cluster meeting at the boundary point where you have this insertion. One cluster because rho can be H13, and two cluster because rho can be H15. So now I can identify, based on such information, the numerator and the denominator of R in terms of the conformal blocks. And from the conformal blocks, I can also generate efficiently the Frobenius series. So basically, I can have an explicit expression for this ratio. So first of all, the numerator is quite easy because if this is, remember, is 1, 4, 2, 3, and if I take the limit in which 1 goes to 2 at the boundary, so eta goes to 0, I generate configuration where I have two clusters which meet at x2. So the only possibility is that this is the conformal block of F15, of phi 15. Because that's the leading singularity, and H15 is the largest scaling dimension, so there are no options. This numerator is the conformal block of phi 15. The denominator is more tricky, but you can understand it like this. So it's a combination of three connectivities. You apply a duality transformation. I'm brief here. But you can think this way. You can apply a duality transformation, Kramers-Vanier duality. So this combination of connectivities is a partition function on a disk or on any domain with this boundary condition for the spin, alpha, beta, alpha, beta. Alpha is a color. And the field phi 13 is in the Cardy, again, you have to go back to Cardy ideas, is the field which implement the changing of boundary condition between alpha and beta at the boundary. So it's boundary condition changing operator in this dual picture. So now if you take the limit in which x1 goes to x2, basically you have a boundary condition which is trivial, which means that the conformal block of phi 13 cannot enter in the denominator. So you basically you can produce only an even number of clusters when you do this OP. And this single out the denominator as a linear combination of phi 15 and identity, which is symmetric under this exchange, x1 with x3. So let me now briefly go to the result. So for percolation, so here are the formulas. So for percolation, R is given by, I can identify, the conformal block of phi 15 that's equal 0. Of course, as I said, the conformal block of the identity is ill-defined at equal 0, but they can solve the differential equation and find the logarithmic solution, which correspond to the denominator, which means that it's symmetric under the exchange of x1 with x3, which is the exchange of eta with 1 minus eta. So there is only one function which satisfies this property, and that it's logarithmic, as a logarithmic singularity. So I can express also G2 and G0 here in this ratio in terms of quite complicated hypergeometric F32, if you want. No, rho is here. Rho is 2 here and 0 here. So G is a function, is G, the solution of the differential equation, which correspond to rho equal 2 and rho equal 0. Okay, but there is a remarkable closed form in terms of hypergeometric, but not discussed, it's quite complicated. So here I want to only to make the point that if you expand the denominator, you see that there is this logarithmic singularity that appears because the solution is logarithmic. And from this, you can identify the parameter B, which was the parameter of Gurarie and Ludwig, as minus 5 over 8. Again, I have to say that this you expect because basically is how Gurarie and Ludwig, they conjecture this value. But here the nice fact is that it appears in a geometrical correlation function that you can measure. And that's the result of the measurement. So you see? So here is Monte Carlo at the points. And the CFT is below, so you don't see it. So you see the agreement is remarkable. Huh? All right, so I'm gonna finishing. So you see here the result of the simulation against the theory, and it confirms, I mean, that I guess that's an exact result. So the same we can do it for Ising, which is Q equal 2, C equal 1/2. We have an expression for this ratio of connectivities. Just the differential equation changes, but again, this identification in terms of conformal blocks remains. So R is an integral of an elliptic function. Essentially, is an integral of an elliptic integral of the first and second kind. So that's a quite complicated formula, so I don't write it, but you can find it. And here is the Monte Carlo simulation against the prediction. You see again the agreement is beautiful, and the logarithmic this function is again logarithmic, has a logarithmic singularity here, and this logarithmic singularity comes because of collision between the null because this is a subtlety. The field phi 1,3 has a null vector at level 2 at C equal 1/2. Which mixes with phi 1,5. You don't see in the minimal theory, but if you extend the Katz table, you have to consider it, and that's this logarithm which appears here. All right, so last slide for a result at Q equal 3 and Q equal 4. Here I can write explicit formulas because they are more compact for R, for the 3-state Potts model and the 4-state Potts model. There is a decreasing complicancy increase in Q. Q equal 1 is the more complicated, and the formula are the more complicated, and Q equal 4 is the easiest one. There is a 1 here. There is a 1 which was cutted, sorry. There is 1 minus. Sorry. 1 minus. Sorry. Otherwise, I think, I don't know why it was cutted here. There's 1 minus. Sorry. Yeah, well, yeah, well, it's better, yes. It has to be. All right. No, I do it right. I did it right. If you put eta equals 0, this is 0, you see? If this 1, there is a 1 here. If eta is 1, this is 1. So there's a 1 missing. Okay? Sorry, thanks. Okay, so, and here for Q equal 4. So here is the result for Q equal 4. So, all right, so you see this is Monte Carlo, and again, the agreement is good. Actually, it's remarkable. Also Q equal 4, which typically is quite complicated. So that's the end of the seminar. I show you that we calculated this 4-point boundary connectivities in the Q-colored Potts model. They have explicit logarithmic singularity at C equals 0 for percolation and C equal 1/2 for Ising. And then we also gave somehow complementary, I would say. It's not really, of course, new because this was already in paper by Gurarie and Ludwig, but I think we gave a complementary interpretation of this B because we show explicitly a correlation function in percolation where this appears, and we show that was measurable with Monte Carlo. I have to say that it's not fully explicit because this B is quite hidden. It's not really, I mean, something that you can measure it, but it's there in the denominator of the ratio. Okay, so thank you.